So now we have already seen how to do a depth first search in a graph. So there is another type of search in a graph which is called the breadth first search or BFS. Or sometimes it is called BFS. So in depth first search, if you have seen already, we are going deep down the level. Before we go, like for this node, before we go to its other children, we'll go all this, we'll visit all this, then we'll come back to its neighbor, other neighbor. So this is the DFS strategy. For BFS, it's just the other way around. You first visit this, then before going to its neighbor, you visit all its neighbor first. Then you come back to this node, visits all its neighbor, then you come to this node's neighbor before you go to the next level. So this is the strategy for BFS. So in a DFS, it's something like using a stack. We have written the DFS actually using a recursive procedure, is it? Now the recursion already uses a stack, system stack. I could have asked you to write the same algorithm without recursion. Then you will see you will need actually a stack to implement the depth first search. We'll see in BFS we don't need the stack. This time we need a queue. So now I'm going to write the algorithm for BFS. This time also we are going to use a timestamp. But this time the timestamp is a little bit different. We are timestamping those nodes which are on the same level with the same timestamp. So basically the neighbors will get one more time than its parent. Okay, so that is the strategy. So the starting node will have the timestamp 0. And that's why everything we are going to initialize with -1 this time. So this is the initialization. For I is equal to 1 to n, do vi dot d is equal to -1 and 4. Then we initialize the started vertex vs dot d equal to 0. Again we have the pi field vs dot pi is nil. Then we initialize a queue. The data structure queue I am just denoting with q. Q is equal to initially the starting vertex s. Then we call BFS with this starting vertex s. Now this BFS will be a procedure which I am going to write in the next slide. So here I am going to write the procedure BFS. BFS is while Q is not empty, do J, you just take out one vertex from the queue, from the front of the queue. So I am putting that one as DQ. Then T is equal to Vj dot, if you go back to the data structure, this should be the adjacency list. So ADJ pointer. Then you go over all its neighbors. While T is not nil, do if V T dot V dot D is equal to -1, that means it has not been visited. Then what should you do? You just visit this. V T dot V dot D should be this time what? V dot D plus 1. So fill up the gaps. This should be J. Vj dot D plus 1. and its pi field also v t dot v dot pi is equal to j, and you NQ this vertex now. NQ QUE NQ T dot V. So you go over the neighbors of the node J and you NQ all this neighbor to the back of the queue if it is not visited, and you take out the vertices from the front of the queue. If you do this, then all the neighbors will be visited first before you go deep down the tree. And this is your end if. Here T goes to T dot next, end while, and this is end while. So this is the algorithm. So what we are doing basically, we are taking a queue. So this is our queue. So when we started with the node S, we are putting its neighbor like this. Then you take out the next one, its neighbor you put here. So you have taken it out. You take out the next one, its neighbor you are going to put. So the ordering you will be getting is just the BFS ordering. If you do this way, and that's what this entire algorithm is doing. So let me just take an example, and with that example we will be done with the BFS. BFS is quite easy. So here is an example, same example again. So let me draw the graph which you have already seen in previous DFS also. We are going to run BFS on the same. So this is say A, B, C, D, E, this is say S. So we are starting with this vertex S here. So when S is, so how does the queue look like? So initially S is there in the queue. So this is the queue. So initially S is there, then we have taken out S. We are going to put its neighbor, say A and B. A and B. So it has a timestamp 0. So A and B will have a timestamp 1. So they have timestamp 1. So once you have done this, then A will be taken out and A's neighbor will be taken, which is C. Its timestamp will be 2. C will be put here. The other neighbor is already there. Now we'll take out B. When you take out B, you will take D as its neighbor. Its timestamps will be 2 again, because this is 1, this will be 2. Now C will be taken out and it will give you timestamp 3. So E will come here and nothing else. B is already there. Now D will be taken out, but if D does not have any neighbor which is not yet visited, then E will be taken out, not yet visited, there is nothing, this call will end. So that this BFS call will end and it will visit only this. So to have a BFS for all the other vertices, what you have to do, you have to give another call on this, fresh call. So you have to run that again the same way. I did not write that outermost for loop. For I is equal to 1 to n, you run over the array, check whether something is not visited, give a fresh BFS call, which I did not write this time. So if I write down the tree now, according to which we have visited, so S is here, whose level is basically 0. From S we visit 2, which is A, which is B. So this is 1 and 1. Then from A we visited C, which is 2. From B we visited D, which is 2. From C we visited E, which is 3. And all the other edges are among this. In this case you can verify these are the other edges. So this time the BFS also makes a tree, and these timestamps are basically saying what are its level in the tree starting from the starting node S. Taking that one as 0, these are the levels. Now once you do BFS also gives you an important information. It is basically the distance of a vertex from the starting node. So for that one I am going to define something. For U belongs to V, define delta of SU as the number of edges of a shortest path from S to U. So basically from S there can be many paths to another vertex, say U. You take that path which is the shortest in terms of the number of the edges. That is called the shortest path. So you would like to know what is the shortest path and what is its length with respect to the starting vertex S for all the other vertices. This problem you can immediately solve if you do a BFS. Basically each vertex timestamp will give you what is the shortest path. So here is the claim: if U is reachable from S, then VU dot D fill is nothing but delta of SU after completion of BFS S. So when you complete BFS S, if U can be reached from S, if there is a path, then the D field is nothing but exactly equal to the length of the shortest path from S to U. So suppose the edge weights are all are equal. You have been given a graph where all edge weights are equal, and we are asking, I give you this source point, give all the vertices, all the shortest path to the vertices. What did you do? Don't run anything fancy here. In this case, just run this simple BFS, it will give you the shortest path. Okay. So that much for BFS. So we have already seen two types of search, depth first search and breadth first search on the graph. And from these two searches we have also found some other applications because it gives you some more structural property about the graphs. Now let us move to another important problem on graphs, which is called minimum spanning tree. Minimum spanning tree, or in short it is also called MST. If V, so what we are assuming is this: the graph VE is connected, this is our assumption, and undirected and weighted. That means each edge has a weight associated with it. What is the spanning tree of the graph? A spanning tree is a subgraph VT such that T is basically a subset of E N is cycle free. So basically spanning tree is a subgraph of the given graph. That subgraph itself is a tree which spans all the vertices, and that's what our notation VT here. T is a subset of E and it spans all the vertices because I have taken V here. And why is it a tree? Because it's a cycle tree. That is called a spanning tree. And what is a minimum spanning tree? A minimum spanning tree MST is a spanning tree VT that minimizes the total edge weights. That minimizes W of T. What is the weight of that spanning tree? Is basically the summation of all edge weights UV, where UV belongs to T. So you take a spanning tree, its weight is nothing but summation of all its edges. And what is a minimum spanning tree? It is that tree, that spanning tree which has the minimum weight among all possible spanning trees. If the edge weights are different, then the minimum spanning tree is unique. In certain cases there can be more than one minimum spanning tree. Okay, but most of the cases the minimum spanning tree will be unique, not always, of course. Now, given a graph, how to find a minimum spanning tree? How do you find a spanning tree of a graph? How do you find it? How do you find the spanning tree of a graph? So when you say remove non-tree edges, what do you mean by non-tree edges?
Start to DFS from different places and take a
So he is suggesting start DFS from different places. I don't know what are those different places. Different nodes. So there are n nodes. So what are those different nodes? So you have to specify very precisely what are those things. So how do you find a spanning tree? You almost are there, but you are not saying it exactly correctly.
So each component there should be at least one
Tree. So what you do? Just run a DFS. Just run a DFS and only retain the tree edges. That will give you the spanning forest if the graph is not connected. But if we assume it is a connected graph, you just run the DFS and take all the tree edges. That will constitute a spanning tree of the graph. But it is not a minimum spanning tree of a graph. Mind that. We are trying here to compute the minimum spanning tree of a graph. People often get confused with spanning tree with minimum spanning tree. Spanning tree is just a tree which spans all the vertices. Minimum spanning tree is a harder problem. So there are two algorithms for computing the minimum spanning tree. One algorithm is called Prim's algorithm. Second is called Kruskal's algorithm. So there are two algorithms. We will study both. But before we study both of these algorithms, what we will do, we will study this construction in a very abstract sense. Okay. So we will study a very general framework of constructing a minimum spanning tree. Then we will see how these two different algorithms are followed from this general framework. Just a variation of this general framework will give these two different algorithms. So first we are going to now study a very general framework for constructing the minimum spanning tree. So we'll develop this general framework stepwise. Initially probably I will not tell almost anything, it's a trivial statement. But slowly we will unravel this trivial statement and non-triviality will creep in. So first what we need in the algorithm is this. We will construct or we will choose a set of edges from the graph such that this particular invariant is always maintained. What is that invariant? The set of edges is guaranteed to be a subset of a minimum spanning tree of the graph. So suppose you can guarantee, suppose in your algorithm you can show every time you are choosing an edge that is guaranteed to be a subset of a minimum spanning tree of the graph. If you can maintain that invariant throughout your algorithm, at the end of your algorithm you must be computing all the set of edges of a minimum spanning tree. So this is our invariant. So you must be thinking, I have not told anything new. Yes, I have not told anything new. That must be the case in any case. But let's put it that way. A is a subset of the edges E is always subset of some, there may be more than one MST, I already told you, some MST of the graph E. This is our invariant which will be maintained by the algorithms. With respect to this set A, we are going to define something. An edge UV is called safe. It is safe for A if UV does not belong to A. So far we have chosen a set of edges which we are sure that they are included in some minimum spanning tree. Now I take another edge UV which does not belong to this set A yet. We say that edge is safe if it does not belong to A and A union this edge UV also satisfy the invariant. What does that mean? It means when you include the edge UV in the set A, the new set A union UV also is a subset of some minimum spanning tree. Then you call the edge UV safe for A. That's a very natural definition. Why it is safe? Because it is safe to include it in the set A.
But that some MST must be same for
All different edges.
Sorry, I could not follow what you were
I
saying.
think that A union UV should be invariant for some MST.
Right.
But that some MST should be constant for a particular. It should be the same MST.
No, it may not be the same MST. Some MST. Invariant is not saying that a particular MST we talk about, but it should be part of some MST. Because in the algorithm we should be able to compute some MST at the end. Okay, so now I am going to give you the algorithm for computing the MST with these two definitions. And you will see actually algorithm is not saying much. But nobody can claim that it is incorrect. Initially the set A is empty while A is not a spanning tree. How can you verify A is not a spanning tree? Very easily. Right, number of edges should be V minus 1 or N minus 1. Immediately you can say it is a spanning tree. While A is not a spanning tree yet, do find a safe edge UV and A becomes A union UV end while. That is the generic method for computing the minimum spanning tree. But you can see the main problem is to choose this step, find a safe edge UV for A. The entire problem I have put under this statement. I have not explained how to do this. If one can give you this, how to do this, we have got an algorithm. And Prim and Kruskal's algorithm, they just give you two different techniques of finding a safe edge. But this is the generic method. Now for this, I define another definition, another term. A cut is a partition of V in W and V minus W is a partition. So what does it mean? So you just take the vertex set of the graph V, you just divide into two parts. One is W, another is V minus W. That tells you it's a cut. Any partition is a cut. That's the definition. So can you see this? How much can you see up to this?
Union basis.
Okay, so I'm going to write it here. Cut is a partition of V where V is equal to W union disjoint union V minus W. So W and V minus W will give you a cut. You're just dividing the vertex set into two parts. Now again another definition. A cut W disjoint union V minus W, we say respects, the cut respects the H set A if there is no edge in A such that no edge say UV, no edge UV in A such that U belongs to W and V belongs to V minus W. Then we say the H set A respects this cut. Why is it called respects? What does it mean? It means all the edges of the H set A are either from the set W or from the set V minus W. It does not have any edge which goes from one set to the other set. Okay. Suppose there is an edge from one set to the other set, then we say it crosses. So an edge UV crosses the cut if one vertex belongs to W and the other to V minus W. So these are the definitions. So using these definitions, we will next see how can we choose some safe edge. So next claim is this. So here is the next claim, which is the main claim for constructing the minimum spanning tree. Let A be a subset of some MST of the graph VE. Let W V minus W be a cut that respects A and let UV be a crossing edge that minimizes WUV, then UV is safe for A. So this is the claim. So read this claim. There are several conditions. First, A is a subset of edges where you know that this subset of edges is a subset of some MST. Already you know that. And you have taken a cut W and V minus W which is respected by this edge set A. So what does it mean? We have this cut W and V minus W such that no edge of A belongs to crosses this cut basically. Okay, if it happens that way, then look at all the edges which crosses the cut and take the edge with the minimum weight in those edges, and that edge must be safe for A. So once we know this claim, we know how to compute a safe edge for A. We know what is A, we just take a cut. For that cut we know what are the edges which are crossing that cut. Look at those weights of those edges, take the edge which is the minimum weight, and that edge must be included in the set A because you know that is safe for A. So I am going to now prove this.
So please explain this.
Yes. So I am going to, so he has asked me to explain this claim once again, so I am going to explain it once more. So what we have done, so suppose we are saying A is a subset of the edges which is a subset of some MST, so it belongs to some MST we know. Now you take a cut which respects this A, so maybe cut is something like this, so there are edges like this. So this is a W, probably this is V minus W. Just it may be that some part of the A also belongs to here, so here also it may be A. But there is no edge which is belong to between the two partition which belongs to A, because this cut respects A. That's the definition of respect. Now what this claim is saying, look at these edges which are crossing this cut. From these edges you take the edge which has the minimum weight. So suppose this is the edge which is the minimum weight among all these edges. We are saying this edge is safe for A. So if you take A union this edge, that new set also is a subset of some MST. That's this claim is. Have you understood everybody? The claim is very important. It's long, but it's saying this, exactly this picture. Now we are going to prove this. How do you prove? Consider an MST Vt with A is a subset of T. We already told that's the condition. A is a subset of some MST. We have taken that MST Vt. If UV belongs to T, we are done. The edge UV which we have chosen, that is the edge which has the minimum weight among all those ones which are crossing the cut. If that belongs to this MST, we are done. We have nothing to prove. Then you can take A union UV which also belongs to MST. So suppose it is not the case. So otherwise we are trying to prove by contradiction. Suppose it is not. Otherwise consider the graph defined by T prime which is equal to T union UV. So you just take the edge UV, union with T. T is a minimum, a set of a minimum spanning tree. What you will get? You will get a graph T prime. I don't know whether that is a tree or not. Yeah, but it's a graph. So I am calling it as a tree prime. Now there is a unique path from U to V in T. If you remember, in the spanning tree T, from any vertex to any vertex there is a unique path. That is true for any tree. Between two vertices there is a unique path between any two vertices in a tree. Always it is true. So you have taken the minimum spanning tree T, and you have taken the vertices U and V. There must be a unique path between them. So let xy be an edge on this path that crosses the cut W V minus W. So the picture is something like this. So we have U here. So there is a unique path from U to V in the spanning tree. So U and V is here. So something else is going out like this, but there is a unique path. So suppose we have taken X and Y, there is an edge. So you have taken, there is a XY be an edge on this path that crosses the cut. Because why it should be? Because U belongs to one part of the cut, one part of the partition given by the cut, V belongs to another one. So it must be the case there is another edge like this on the spanning tree. So let XY be that edge. Now you already have seen, so XY also crosses, UV also crosses the cut. UV also crosses, XY also crosses. Now UV is the minimum edge weight among all those edges which are crossing the cut. So it must be the case that WUV is less than WXY. So if it is the case, what you can do, you can delete this XY and put UV back. So it will make nothing but the tree, another tree. So from the tree what you have done, you have just taken out XY and put back UV. So in terms of the tree, if I just draw, so suppose this is U, this is V, there is a path like this. So tree is something like this, it goes on, let's say. So what I have done, so there is a XY edge, you take out this XY and join this. This also becomes a tree. This also becomes a tree. So what you have done, you have created a new tree now, which is also spanning tree, but its edge weight is less than equal to the previous tree's edge weight, less than equal to. Because you already told that UV is the least weight edge. So weight of UV is less than equal to weight of XY. So if you delete XY and put back UV, what do you get? The new weight of the spanning tree will be less than equal to the previous spanning tree. But your previous spanning tree is a minimum spanning tree. So this one cannot be less than the previous spanning tree. So it must be the case that this is also a new minimum spanning tree. So that means UV also belongs to a new minimum spanning tree. So that's why UV is safe for A. So let me write it down now. So thus W of UV is less than W of XY. Now define the new tree T double prime as T prime minus XY. Now T double prime is again a spanning tree of V, and furthermore weight of T double prime is equal to W of T minus W of XY plus W of UV. But we know W of UV is less than equal to W of XY. So this means this is less than equal to W of T. But T is a minimum spanning tree. How can you have another T prime, double prime, whose weight is less than W of T? It cannot be. It can be at most equal. So this means, so V T double prime is an MST in that case. So if UV does not belong to a spanning tree that T, then either there is another minimum spanning tree to which UV belongs, or the entire assumption is not true. In either case, UV is a safe edge. So this is the proof, and this is the reason why Prim's algorithm and Kruskal's algorithm work. They have given you an algorithm, but the first question is, why should that algorithm give you a minimum spanning tree at all? That proof has to be there, and this is the proof why it works. But this is a very generic proof. You don't have to prove Prim's and Kruskal's algorithm differently. What it is saying, if you have a partition, if you have a cut, and you have a set of edges already which belong to the minimum spanning tree, one minimum spanning tree, you find out a cut that respects those edges. Take the minimum weight edge which crosses that cut. That edge must be safe. You include it in your set. Those of you who knows Prim's algorithm and Kruskal's algorithm, you will see both of the algorithm does exactly this. In Prim's algorithm, it tries to develop one tree, tries to grow one tree to a minimum spanning tree. Every time it chooses the minimum weight edge which is not yet there and which is basically a cut, crosses the cut. And Kruskal's algorithm, it develops several trees and ultimately merges all this tree into a single tree. But while merging, it chooses those edges which are the minimum weight edge among which crosses the cut. So in a sense both are same, but they are just choosing this safe edge differently. So in the next class, we will see these algorithms and we will see how we are choosing these safe edges for this.